66 million years ago, Earth was ruled by giants. Then, in a single catastrophic moment, most of the planet's species collapsed, around 3/4 of life wiped out almost at once. The impact came from an asteroid roughly 6 to 9 miles wide, blasting into what is now Mexico and leaving behind the enormous Chicxulub crater. But here's the shocker: survival wasn't about being big or fierce, it was about being small, flexible, and lucky enough to adapt. Why did crocodiles swim on while mosasaurs sank into extinction? Why did birds endure while their towering cousins vanished? To understand, we need to look at the world they thrived in right before everything changed. In the last chapter of the Cretaceous, the world was still dominated by giants. Tyrannosaurus rex stalked broad floodplains, herds of triceratops grazed across open ground, and slow-moving ankylosaurs pressed through forests armored against attack. Offshore, mosasaurs used their powerful jaws and muscular tail-driven swimming to chase fish turtles and ammonites. To anyone looking in life, seemed secure an empire of colossal creatures balanced at the top of their environments. Yet just beneath the surface, strength carried hidden fragility. On land, ecological networks appeared stable but were deceptively complex. Large predators occupied extensive territories, shaping the movements of other animals. Vast stands of flowering plants were now common in many regions, with angiosperms providing food and cover in ways that had begun to reshape ecosystems. Insects pollinated them, small mammals raided seeds and fruits, and some early birds tested new feeding strategies near their edges. This interconnection made the system look tightly woven, but dependence on specific food sources also amplified risks. When one part faltered, everything tied to it could be dragged down. The oceans showed similar contradictions. Mosasaurs ruled as apex predators, but their survival ultimately relied on prey chains built from plankton blooms and vulnerable ammonite populations. Ammonites spawned countless small offspring that drifted through the water column, a strategy that thrived in stable conditions but collapsed when environmental stress disrupted productivity. In contrast, lineages like the nautiloids, which produced fewer larger young, had a buffer that gave them better odds of surviving downturns. Vast marine webs funneled energy upward, but the foundations were narrow, and when they shook, the giants above had no backup plan. Even before the asteroid impact, instability was already spreading. The Deccan traps in India erupted forcefully, releasing lava and gases that altered atmospheric chemistry. Sea levels also rose and fell in irregular pulses, shrinking the shallow coastal zones where marine biodiversity concentrated. Long-running volcanic eruptions and shifting seas stressed ecosystems in places, weakening certain food webs long before any object struck from the sky. What looked like permanence was in reality already under strain. Alongside the giants lived smaller, easily overlooked groups. Mammals crept through roots and undergrowth, remaining mostly invisible to the towering creatures above. Crocodilians lingered in rivers and swamps, using ambush instead of endurance to capture prey. Turtles, lizards, snakes, and early birds filled scattered niches, many of them less dependent on constant abundance or fixed diets. While the dinosaurs and mosasaurs embodied grandeur, these modest lineages survived in quieter, more flexible ways. In the end, the Age of Giants was not undone purely by overwhelming force, but by the fragility of systems that had seemed invincible. They were powerful only so long as sunlight reached the forests and plankton flourished in the seas. When disruption came suddenly from above, that foundation collapsed, and what followed next was not a reign of strength, but a world choking on darkness, where survival itself became a minute-to-minute struggle. The impact left behind not just a crater, but a planet transformed into an ash-choked world where survival meant enduring conditions no ecosystem had faced before. Imagine stepping outside and seeing the sun vanish behind a thick veil of dust and vapor. The warmth faded and the plants around you began to fail. The air carried a sting that burned your throat, evidence of the chemical changes unfolding globally. The first moments after impact were violent on a scale beyond comprehension. Shockwaves tore across continents and tsunamis surged into coastlines. Many researchers model a brief but intense thermal pulse that likely ignited regional firestorms, though whether these fires spread everywhere is still debated. Debris heated as it re-entered the atmosphere, striking the land and boiling the surface of lakes and seas. Vaporized sulfur from the target rocks formed aerosols that created acid rain and helped acidify the oceans, adding yet another layer of stress to already collapsing systems. But the most widespread, long-lasting consequence for food chains was not the initial violence. Dust soot and sulfate aerosols blocked sunlight, driving what scientists call an impact winter. Models and sediment records indicate sunlight may have been reduced by more than half for months to years, and in many areas, photosynthesis failed entirely for extended periods. Plants ceased producing energy, plankton blooms collapsed, and the ecosystems built upon them unraveled in a cascade. For large animals, this was an unavoidable trap. A multi-ton hadrosaur required mountains of vegetation just to sustain itself. Apex predators like Tyrannosaurus needed vast hunting ranges filled with prey. Once the primary producers vanished, so did their prospects for survival. Gigantism, once a key to dominance, became a burden that offered no way out of famine. Smaller survivors, in contrast, hid important advantages in their biology. Ground-dwelling birds that could eat seeds tapped into food reserves packaged to last through dormant seasons. Seeds persisted even as foliage and fruit supplies disappeared. Insect-eating birds also had a chance. Insect populations could ride out the catastrophe by feeding on decaying matter. The distinction proved fatal for other birds with teeth. Highly specialized diets or inflexible feeding strategies failed. Success no longer favored size or flight power, but adaptability at the dinner table. Waterways, lakes, and marshes provided a different kind of refuge. Crocodiles, capable of fasting for long stretches and scavenging whatever washed their way, remained in rivers. Amphibians could slip into underground burrows or reduce their metabolism in mud at pond bottoms. Turtles with slow metabolisms and protective shells endured both hunger and predation. Many of these aquatic communities relied more on detritus, dead organic matter flowing downstream, than on living plants shielding them from the same collapse that decimated terrestrial webs. Cold-blooded reptiles and amphibians further benefited from their ability to reduce energy demands, surviving when endothermic giants required fuel that no longer existed. By the time the atmosphere began to clear, the most dominant species were gone, leaving behind landscapes with empty roles. In those vacant niches, the overlooked survivors now carried the future of evolution on their shoulders. And among them were small mammals, whose hidden traits had already prepared them for what came next. How did small, unassuming creatures rise to dominance in a world emptied of towering reptiles? At first glance, the shift seems unlikely. Mammals at the time of the impact were modest, mostly rat-sized forms clinging to survival in burned landscapes. Yet when the giants were gone, those same creatures began to occupy the empty spaces, gradually building the foundations of new ecosystems. Mammals had endured more than 100 million years in the margins while dinosaurs ruled. They occupied hidden spaces, burrows, tree roots, and wetlands, and much of their activity occurred under the cover of night. Those same strategies cushioned them against the disaster. Traits such as nocturnality, burrowing habits, flexible diets, and relatively small size allowed them to handle low light, extreme temperatures, and patchy resources better than many other animals. Smaller size and shorter generation times compared with large dinosaurs probably helped mammals rebound faster, though precise reproductive rates for dinosaurs are hard to compare. The evidence in the rocks shows just how fast things changed. Fossil layers in Montana and New Mexico reveal placental mammals appearing within the first 100,000 years after the boundary. That is almost immediate on a geological clock. In fact, within roughly 700,000 years, some mammals reached around 110 pounds, an enormous leap from the tiny survivors. The Paleocene site of New Mexico preserves the genus Ectoconus, one of the largest mammals of its time, showing how quickly lineages could grow far beyond their starting scale. This burst was not simply about becoming bigger. It was an adaptive radiation with lineages branching into diverse roles. Some remained tiny insectivores, while others shifted toward herbivory or carnivory. Early placentals displayed a variety of limb structures, with some adapted for climbing, others for running, and still others for digging. Teeth records show a wide spread of diets developing in just a few million years, suggesting mammals were experimenting with every available niche at remarkable speed. Plant life was crucial in fueling this expansion. Angiosperms, already widespread during the late Cretaceous, rebounded quickly as the skies cleared. Fruiting plants offered energy-rich resources that supported omnivores and herbivores alike. Seeds and nuts carried over from lean seasons, giving rodents and other small mammals reliable options. Larger herbivores, in turn, could tap into the new leafy growth. The diversification of flowering plants and mammals went hand in hand, each driving opportunities for the other and transforming Paleocene ecosystems into complex layered communities. The pace of change surprises nearly everyone who studies it. Within just a few million years, mammals occupied roles as predators, foragers, and grazers on a scale unmatched during the age of dinosaurs. Some lineages began to shift activity patterns away from strict nocturnality, opening windows for new behaviors. These early experiments in body size, lifestyle, and feeding shaped the path toward primates, ungulates, and eventually the rich diversity we know today. So those tiny survivors didn't just persist, they reshaped entire ecosystems. And this was only the beginning of a deeper reset in the story of life on Earth. The extinction was not just an ending, but a reordering of life's rules. Size and strength lost their power. Resilience and flexibility determined who endured. Birds, crocodiles, turtles, amphibians, and small mammals carried traits that let them weather the catastrophe and laid the foundation for the biosphere we know today. Remember, the impact triggered an impact winter, shutting down photosynthesis and collapsing food chains. Survivors were those whose diets, metabolisms, or refugees were less tied to active plant growth. Which survivor do you find most surprising? Birds, crocodiles, or tiny mammals? Share your thoughts below, and don't forget to like and subscribe.